Okay, so yeah, um, hopefully your summer is going well. Yeah, so I haven't done this in a while, but let's talk about like the course, right? It's going to be like Calc 1. Um, so like many of you could have had some encounters with calculus before, and others could know nothing about it. So, like obviously, we're not assuming anything specific about calculus, so we will start from scratch. Um, but at the beginning, like some stuff may look a little bit repetitive, depending on whether you have seen some of these things. But it's like any summer course, we'll meet except for like special weeks, like when we have holidays or things like that, we'll meet like 4 times a week. So obviously it's going to be faster than your regular course, but I mean it's still doable, of course, as long as you focus on this. Um, you know. So it's just important to be aware that you have to keep track of what we're doing on a like almost like on a daily basis, right? But it's not like, I mean, but it's still like a manageable amount of material if you pay attention. So I think what I was planning on doing at the beginning today was just like mentioning a couple of things about the syllabus because our class is online. We also have to discuss like the grading, how that's going to work, and then give you like an introduction to what we will cover in the course. Maybe it starts with some of the material, things like that. Feel free to interrupt me at any time. Either if you prefer to unmute yourself, that's great, or you can also just type it on the chat. And on the chat, like, either a public message or a private message, whatever you're more comfortable with. So I think maybe I should show you first the syllabus. Oops. Oh, yeah. Okay, so can everyone see the syllabus? I believe you can find it on Canvas, just in case. So yeah, everything good? Can you see it? Okay, so yeah, so typically our meeting times will be until 3 p.m. The idea is not to necessarily make it like a 2 hour long lecture, like from time to time. Well, as I'll tell you in a couple of minutes, we'll have some quizzes and also like we can insert some like more like types of activities so that you like, because 2 hours is kind of a long time for like a lecture. And also probably we should do like a break or so when there's like a natural transition between different topics. But at least like our meeting time is from 1 to 3, and then like for the office hours, I just figured like the easiest thing would be to do them right after class. So like rough, I can save more time if there are more questions, but roughly like like at least like half an hour every day after class. The Zoom link will be the same as the one that you're using for joining the lectures. So I thought that was the easiest thing. And as I said, I'll be recording the lecture. So I'll once like we finish like with the lecture, I'll upload the video and send you the recordings. Uh, so about the textbook, well, there's if you want to see like a physical copy of the book, this is it. But you don't really need like the physical copy because for the online homeworks, we'll be using MyLab, which maybe some of you have already dealt with in the past. And MyLab comes with a electronic version of the book. So I'll show you MyLab in a couple of minutes so that you see how it's supposed to look like. And roughly, we will discuss like these chapters from the book, like the chapter 1 about functions. It it is kind of pre-calc stuff that you probably already saw. So like instead of like just starting with chapter 1, like for 1 or 2 last uh days, like what I'll do is kind of like whenever we need something from chapter 1, I'll mention it like some sort of like introduction, and then we'll do like the necessary calculus stuff that we wanted it for, instead of like just spending like a couple like of days just in chapter 1. So you'll see what I mean by that. in a couple of minutes. And yeah, like this is more important, like a tentative schedule for our class. So yeah, so for like at least for week one, which is our current week, um, the idea was like we'll have probably like a short quiz on Thursday. I'll give you more information about the quiz tomorrow on what that should be on. Typically, what I'll do for the quizzes is like I'll give you like a list of problems just to make it like say 10 or 12 problems, 15 about the number, and like the quiz would just be some like two problems from that list. Like I'll copy paste it. Like it would be completely the same as it would be just like I will just choose some two like around two problems from the list that I give you to look for. Okay, so hopefully that'll help release some of the tension, and like that way I guarantee, everyone then has the incentive to do every problem on the list. So I'll kind of try to select like a good sample, like a representative sample of like the topics we cover. Okay, so for the quiz on Thursday, I'll probably give you tomorrow, like, or maybe today. Give you like a preliminary list of what to look for, and then like the quiz will just be up from there from that. Yeah. Um, and again, we'll have some exams. Well, I shouldn't even call them midterm. So we'll have some exams. I will give you more information about that when the time comes. Like the important thing is that for all the quizzes and the exams, since our class is online, we'll do something. The proctoring, the way it will be handled is using something called Respondus, which I don't know if you have seen it, but it is some sort of like lockdown browser. Um, so what I'll do is kind of probably today create like an assignment or like a quiz. It won't have any grade. It's just for you to get acquainted with how this browse responders is supposed to work. So I'll create like a quiz for you to take it, just so that you know kind of like how the environment is set up. Like I think usually when you log in, you have to like it will ask you to scan your environment or to use like the webcam to show what's around you. And then the idea is like on a typical exam or quiz, after you're done taking the quiz or the exam, you'll take some pictures of your work, of your written work, and upload it as a PDF, preferably to Canvas, and that's what I will grade. Is that making sense? Maybe I should stop here because this is kind of where always like there can be some questions about this.
I actually just have a
Mhm,
question about that.
mhm, mhm.
So I take all of my notes on my iPad.
Uh-huh.
So will I still be able to upload as normal?
Mm,
Because I've
so
never like uploaded any notes really like in this way. So I'm just wondering how that will work.
No, so you really get some paper. So for the quizzes, I mean, for the quizzes, I don't care too much, but for the exams, like, yeah, the idea is like everything should be handwritten. So you should like, take the pictures. I mean, you could use your iPad or your cell phone to take the pictures of it, of course, but I'm just saying like that should be handwritten, if that makes sense. So yeah, even for the quizzes, I will tell you just to practice like doing it on a piece of paper. But for the quizzes, I don't care too much about that because I will be giving you like the questions like that will be on the quiz. So it's not that I'm too worried about that. But on the iPad, it's kind of like the problem with the iPad is that once you have the iPad, everything is kind of like available to everyone. So it's kind of like it would always make it like an open textbook type thing, which is the exams are not. So that's why you cannot use the iPad. Does that make sense? Does that make sense?
Yeah, clears up. Thank you.
Mhm. Any other questions? Okay, so just to show you about this, like MyLab, that can also be useful. Let me see if I can share the screen, the Canvas site. Okay, this is what happens when you have a lot of tabs open. Where is Firefox? Oh, here it is. Okay, so just in case, like, all right, this is our Canvas site. Yeah, you can check the syllabus here. I created like an assignment. I won't, I mean, it's kind of optional if you want to write something about yourself, just to have like an idea of who's taking the course, what you're interested in. I think it's kind of useful for everyone to maybe have like a common group chat. So if you end up creating one and just want me to share the link or whatever, I'm happy to do so. But especially since the course is online, it's kind of hard to create like a sense of like community or whatever. So if you have ways to just like communicate with one another, that would be good, I think. So if you end up, yeah, creating, if someone ends up creating like a, oh yes, there's a question or someone raised their hand. If you want to type it on the chat or you can ask me, unmute yourself. Um,
Hey,
yeah,
can you hear me? Cool.
I can.
I was a little bit. What do you want the video cameras on or off during class?
Oh no, it's totally up to you. If you want to turn it on, that's great. If not, that's fine as well. Yeah, so it's kind of like optional. Also in fact, like this is a good like excuse to mention this. Like in a sense, like the attendance, it's kind of like optional. Obviously, like for the quizzes and things like that, I do expect people to show up. But I mean, that will always be like towards the end of the lecture. So if someone needs to show, like what I'm trying to say is, if someone comes late or they just need to for 30 minutes, they need to leave the meeting or whatever. Like that's totally fine. I won't be I won't be keeping track of attendance, although of course, like the more you can be in person, the better, because that's when you can ask questions. But I'll always be recording the meetings and everything and sharing the video. I'll also share like whatever I write on the iPad with you. So but yeah, like so during like regular class time, like yeah, you don't need to like turn your camera on. Is there any other questions about this? Okay, so right, what I was saying is that yeah, so if someone ends up creating like a group chat, just let me know. I'm happy to share the link so that you can all join it. Right. So for now, where is it here? Okay, so if you click on Access Pearson, that's what you have to use to sign up to the MyLab or the online homework of the class. So what you will end up seeing is, okay, I need to open, maybe that may not look exactly the same for you because like I'm using it from the instructor perspective, but this is more or less how this will look like. So for example, let's see, I believe I created like I already posted like an assignment on MyLab. Okay, let's see, of course. This is okay, yeah. So there should be like an assignment which is due. Why is this so inconvenient? I'm trying to see. Oh, okay, but where is I'm trying to look at it from a perspective that looks manage assignments. I think this will be better. Okay, yeah. There's like an assignment, for example, that's due on Thursday, which is June 1st. And another one that's also due on Thursday. So more or less the idea with these assignments is that roughly, it's like many of the problems are just kind of like warm-up problems in the sense like they may and like just to practice some concepts. I'll also be providing you like kind of more like kind of something like along the lines of old practice exams and things like that, so that you have like a better idea of like how the actual exams will be structured. But some like, so what I'm trying to say is like these online assignment problems are kind of like on a spectrum. Some problems can be very easy, others will be like kind of like exam type problems. So just be ready to like see like all types of difficulty on these assignments. Like what I'm doing for this problem is like if like the way I'm putting the settings for each assignment is that if you don't finish like all the problems by the due date, you can still work on the assignment and no points will be deduced. So like in a sense, so late you can do late submissions. That's okay. Obviously, just try to do as much as you can by the deadline. But yeah, there's not a problem if you go past that deadline. And I'll probably by the end of the, I mean, I'll have to decide on a percentage, but I'll probably do something like, if you complete like 85% of all the problems on the assignments, then I'll just like give you like the perfect score on these assignments. So I'll kind of do like a curve so that you don't have to finish like all the problems. But yeah, like many of them will be very relatively straightforward, and others, especially as when the course begins, like as the course progresses, like some will be harder to do. But I think like the earlier problems will probably be relatively easy. But yeah, this is and like if you click on here on eText, that's how you'll get access to the online version of the textbook. Is that making sense? Any questions about this?
Hey, in order to use the online textbook, will we need to buy it on MyLab?
Yeah, so I don't remember the price, but yes, you will have to purchase the access. Depending on your plans, like there's like an option of purchasing the access for like a year and a half or something like that. That's because, assuming that you take the sequence of Calc 1, Calc 2, Calc 3, you will be using the same textbook. So there's kind of like a discount if you buy like the year and a half option. But if you just plan on taking Calc 1 for this semester, or well, not the semester, but for the summer course, then you may just purchase the access. You may just purchase the access for these 2 months. But yeah, like you do have to purchase something. Yes. Is that
Okay,
so?
thank you.
Yeah, sure. But yeah, like depending on what your plans are, it may be more convenient to purchase like the longer time access. Any other questions? Okay, and then there I haven't posted much else on the Canvas website. I mean, I have taught this class in the past. I taught it like at the University of Virginia. So from that time, I had created like some study guides or work material. So like that's what I posted like here. If you, sorry, I should go back. Like if you look at it, like this is where it says material from old course. So yeah, so if you click on these PDFs, like you'll see some summary of like the basic stuff we'll cover on calculus. I mean, some of like this preliminary stuff is kind of like more like pre-calc stuff. So it's not that you have to again like use all we won't be using all of this at once. So this is something you may come from time to time to refer to it. But some like it has some like these guides have some problems. I also posted the solutions on a different PDF that you can also see there. But so sometimes I'll be like, well, for this quiz, I'm interested. Check out these problems from this PDF as well. So things like that. So I'll be referring to these study guides or these PDF guides from time to time. Just when I want to recommend problems or other things. I probably will also give you like a study guide for each midterm or for each exam as well. But that will be a little bit later once we decide what topics to cover for each exam. So that okay? Yeah, I think this is more or less everything that I wanted to say before, like kind of starting with the course per se. So I don't know if anyone has like a question before we begin.
Having
Mhm.
I've never used the homework website. So if like I were to make an account with the school email, how would I like get the assignments?
Mm, well, I think like it should be relative. I mean, if you go through Canvas, through the course website on Canvas, like I think it's will be relatively straightforward. But I mean, if someone is running into issues with the MyLab part of it, you can just email me, and then we can deal on a case by case basis. It's like the thing is like from the student perspective, I've never like purchased the access, so I don't really know how it looks on your end. But this is where like the group. This is kind of like a perfect like example where I feel like the group chats can work because other students like are buying the act like are creating their accounts and things like that, so they can give more insight. But yeah, if someone is getting stuck with the MyLab, just shoot me an email and we can see what to do. But I mean, I think for the majority of cases, like if you just go through the Canvas side, it will like once you like it will tell you, do you want to sign in for this course or this class, and that's like almost automatically you have access to all the assignments. But again, there might be some variations because I know some of you maybe have purchased MyLab before and things like that, so you just want to transfer the code. But yeah, in those cases, I would be like, you can email me and like you can explain your situation. There's like we have a very useful, good support from MyLab, so that any special cases that arise, we can handle them. But again, like it's not a problem, so I wouldn't be too worried. I mean, yeah, hopefully we can resolve it by today or tomorrow morning, but so that you can access the assignments. But yeah, I would say in general, if there are any problems with MyLab, or explaining, just take some screenshots of what you're seeing, and then I can more easily help you. Even during office hours, this is something we can go over because then like you can just share your screen, and then it's easier for me to tell you, or do this and do that, if that makes sense.
Thank you.
Yeah, sure. Any other questions? Okay. Oh, good question. So there's another calculus course called 135. This course, in fact, this course is more or less almost the same in terms of the topics that we cover. Like there is some extra detail or maybe slightly more difficult questions, but for like the majority of the overlap with this math 135 is like at least what 90%, I think, of the topics they just happen to agree. So yeah, it's very much like the same to that course. It's just sometimes we'll go into more details for this one, but yeah, there's not much of a difference. In fact, like there's some again, once we get closer to the exams, I'll probably send you some links from all exams, and some will be from 135 because many of the problems would just be useful for this class. But yeah, 151, like again, like the target audience, I think it's more like people who will be interested in physics or math or engineering, things like that. The other could be more like biology or like medical science. I suppose I would need to check like what the target populations are. But that's why our calc one is called for math and physics, or the physical science, I guess. Good. Any other questions? Okay, so I thought that like for today, Let's see. I mean, so for today, like, first, I just wanted to give you like a relatively small introduction to what we're supposed to do in calculus. And then, again, maybe we can do like a mini break, 5-minute break for people to just go to the bathroom, take some water, whatever you need, coffee. And then we just can continue a little bit, starting the material. Again, like, depending on the day, I'll try to do something more interactive, but at least for today will be more like just like a regular lecture. So again, like maybe you already have some experience with calculus or not, but again, I will not assume that you have seen it before. So yeah, calculus is kind of like, one of the most famous parts of mathematics. Like, it depending on where you want to start count, like where you want to start, like parts of it was developed in ancient Greece, other parts in the Renaissance. It really took shape, like it was kind of completed somewhere like in the 18th century, 19th century. But like at its core, like it was trying to solve like very natural problems. So here, let me just mention some problems that it was trying to solve. So and again, I'll share my notes with you. So if you prefer, I mean, I find it useful to take notes like as a way to memorize it, but if you don't want to take notes and just prefer to pay attention, that's also fine. So one problem that was very natural was how to compute areas and volumes. So for example, like, if you have like a rectangle, just to give you something very easy, right? If the length or the size of the rectangle have like lengths x and y, right? Then you know that the area right, you know that the area of this rectangle is x times y. But even something like, let's think of a circle, right? If you take a circle of radius r, oops, no, I didn't color it too nicely. But if you take a circle of radius r, well, hopefully you remember that the formula for the area of the circle is pi r squared, right? But here's the question: why the area of the circle pi r squared? I mean, it's not necessarily that obvious, right? I don't know if anyone actually knows the answer to this question. Or anyone wants to give it a shot. Oh yeah, yeah. By the way, if like sometimes I may miss when someone raises their hand on Zoom, so feel totally free to just interrupt or comment. So yeah, but I think yeah, someone raised their hands. But yeah, sometimes I may just miss that, so just feel free to talk right away. But yeah, if you want to, I don't know who raised their hands, but yeah. You want to
Yeah.
yeah.
Is it just like the radius and the area are just related in that way, and that's just kind of how it is? I don't know.
Well, right, like that's a thing. I think people kind of are just told that that's the formula for the area, but I think the majority of the like in high school or wherever you see this for the first time, they don't really give you like a good explanation for why the area is pi r squared, in my opinion. So in fact, like what I'll do in a couple of minutes is kind of like give you like a flavor of how you can show that, like using like the ideas from calculus. But what I'm trying to say is that already for a circle, it's not obvious what the area is, despite the fact that everyone kind of knows the answer, right? But I mean, you have only been told the answer, right? It is, but my point is that it is actually not clear what the area should be, maybe. So, and then like, so what calculus will do, like actually calculus gives you like a good way, for example, to understand the area of like, to find the area of a circle. And it gives you like even something like more general. So for example, like you could have like the function, like a function y equals f of x. And I'll tell you more about functions in a bit. But if you remember like the graph of a function, that's kind of like some sort of curve on the xy plane, right? And so there's like an area which you can represent between the curve and the x-axis, right? Which is what I'm coloring right now. So there's an area here. And what you'll see is that that area, the way it's computed in calculus is by doing something that's called the integral of f. And again, this is actually kind of closer to the end of the course, so it's not something we have to worry too much about. But what I'm trying to say is that this area is computed by something called the integral, and the way in which this is written, which right now it's just like a weird symbol. It's not, again, nothing to worry about. Is this is what you end up seeing in a couple of weeks, that this is how the area is supposed to be computed. And of course, I'll tell you later what this actually means. But what I'm trying to say is that calculus, you know, gives you like on a first level, it gives you like a way to find all these areas, which doesn't sound too exciting, right? Because maybe you don't really care too much about finding areas. The thing is, like, many problems can actually be reinterpreted as like finding areas. So for example, like, if you know the velocity of a car and you want to find like the total distance traveled, that distance, it can be reinterpreted as finding the some sort of area. So in fact, like in general, like anytime you want to find like a total, like a total amount of something, like total distance travel or total income, total loss, like if you're a company, that depending on the information that you're given, that would be some sort of area. So it's just that many problems can be reinterpreted as area problems, and that's what makes this useful. Otherwise, I mean, sure, like maybe people like finding areas, but it's not just like its only use. Otherwise, no one, there wouldn't be that many people taking calculus ever, right? So many problems just like are interpreted as area problems. So let me just write that as a remark. Many problems Okay. So in fact, okay, maybe before going on, like let me just show you like what the area of a circle is pi r squared. Can be kind of fun to see that, and then I'll tell you more about some other things you can do with calculus. So let's talk about the area of a circle. Let me change colors. So again, I'm going to give you a circle of radius r, right? And I want to find the area of this circle. Okay, and so I'm going to do it in a way that kind of has like the flavor of how this is the way you think about these problems from a calculus perspective. In fact, like this idea kind of roughly it is similar to something that Archimedes did like 2,500 years ago. So it's like kind of comes from ancient Greece. Like this is something that the Greeks kind of knew how to do. So it's like very, 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 very classic thing. So the idea, like if you want like a more modern metaphor, is that you can think of a circle as like a pizza, right? So if you think about it that way, let me see if I can show you this animation. So a circle, you can think of it as representing a pie of pizza, right? And if you have a bunch of friends, right? Well, what you naturally do is split the pizza among all your friends, right? So you start cutting slices, right? So you know if it's only you and one friend, like maybe you cut the pizza into 2 pieces, right? But by the way, can everyone see the animation on GeoGebra? We'll be using GeoGebra a lot throughout the course, so I'll tell you more about it later. But yeah, just checking. Okay, so if you have 2 friends, I mean, if it's only 2 people on the party with kind of a small party, you cut it this way. But you know, as you have more and more friends, you have to cut the pizza into more slices, right? And more or less, this is how the subdivisions start looking like. So far, so good. So hopefully what's clear, right, is that the area of the pizza should be just like, you know, if I'm cutting it into 8 pieces, I should just find the area of one of these slices and multiply it by 8, right? Or if I cut it into 12 pieces, I should just find the area of one of these slices and cut it by 12. Is that making sense? So like I should write it on the chat. I don't want to go back to the iPad yet. So what I'm trying to say is that the area of the pizza is like the area of a slice times the number of slices, or the number of slices times the area of a slice. Is that making sense? I wrote it on the chat. I'll write it also on the iPad so that area pizza equals number slices times area of a slice. Okay. Okay, so some of you gave thumbs up, which I'll take as a symbol that this is going well. So, okay. And this is true regardless of how many slices you cut, right? The thing that happens is that as you cut more and more slices, something interesting starts occurring about how these slices look like, right? So just notice I'm increasing the number of cuts that I'm making, right? And I don't know if anyone can tell me what this slice, what I'm trying to say is that these slices start looking more and more like the like a different geometric shape, right? I don't know if anyone wants to take a guess at an individual slice. What does it start resembling more and more? Exactly, right? Yeah, good. In fact, like you notice that once I have 24 slices, they almost look identical to triangles, right? They're not triangles, right? If you zoom in, they always like they actually always have like a mini arc right there, right? But the philosophy of calculus, right, is that kind of in a sense, if you made smaller slices, or the difference between the actual slice and a triangle is kind of getting smaller and smaller. Okay, and just that you'll see it's enough to find the area of a disk. So let me go back to the iPad to show you what I mean. Okay, so what I'm trying to say is that if so, n is going to be here the number of slices. So the area of the pizza is just going to be n times the area of a slice. But the key idea here, so the key idea is that when you made many, when you have made too many, when the circle, you cut the circle into too many slices, into a lot of slices, and here the key will be a lot, then each slice is very similar to a triangle. So in fact, let me just draw the circle again. Let's say just to make something concrete, let's say I'm going to make this oops. Right, so here I'm showing you what this looks like when n equals 3, right? When I make 3 cuts. So again, like the idea is I kind of think, well, there's actually like a triangle that you see here, right? So what would be the size of this triangle? Let's just focus on one of these slices, right? And again, here we're working with a circle of radius r. So what's the length of these two sides of the triangle? It's r, perfect, because it's just the radius of the circle. Good. Perfect. So this is r, this is r. First of all, that already tells you that the triangle is isosceles, right? Now, the thing is, we also need like to find the area of a, why am I doing this? Because it's easier to find the area of a triangle, right? We kind of know the area of a triangle is base times height, right? So in fact, like, because the triangle is isosceles, the area of this triangle of a slice. I mean, it's you just have to play a little bit with the trigonometry, right? Because if you call this a base for B, the area of a triangle is 1/2 base times height, if you remember that, right? And then you can find the height using Pythagoras theorem. I mean, I don't want to go into too many details at this moment, right? But you have like a right triangle here, and then you can use Pythagoras theorem to find like a formula for H. So if you just believe me, or if you want, you can try it on your own to make sure that this is convincing, right? So that's kind of like the formula for the area that you find for this triangle. Okay, so that's the area of a slice. So basically, the only thing that we need is kind of like let me put this as b over 2. So it's base over 2 divided times the square root. So the only thing that we actually need here is an expression for the base. So what I'm after, right? What I'm after is like a formula that gives me the length of this side. Okay, and now this is where I'm going to use this idea that if I made a lot of slices, right, there's really not that much of a difference between this dark purple segment that you see here and the length of this arc of the circle, right? So the idea of calculus is kind of saying, well, once you made a lot of slices, there's not that much of a difference in the values for the length between these two things. Okay, so what I'm asking is kind of like, what would be the length of this part of the crust of the pizza, right? Anyone has like let's just make this very concrete, right? If I'm making 3 slices, right? If I'm making three slices here, what's the length of each of these arcs? Anyone knows? Excellent, right? Like the thing is, like these 3, that's why I changed the color to red, right? These 3 arcs make up the crust of the pizza, right? So they make up the perimeter of the circle, right? And if you remember the perimeter of a circle is 2 pi r, or pi times the diameter, right? So each slice is getting a third of it, right? So each red slice here is 2 pi over 3, 2 pi over 3, 2 pi over 3, 2 pi over 3. And the idea is that if you made n slices, right, with n slices, I mean, it's essentially the same formula, except that now you're dividing by n instead of 3. So what I'm trying to say is that I'm going to take b to be 2 pi r over n. And again, that's not 100% true. The thing is that it is a better and better, it becomes more and more true in a sense, the more slices you made, right? So it's not that the purple segment is the same as the red segment in length. It's just that the difference between the two kind of becomes smaller and smaller as you make more and more subdivisions. Okay, so if you do that, what does the formula for the area become? It becomes 2 pi r over 2n times r squared minus b squared. B squared becomes 4 pi squared r squared over 4n squared. So I'm just substituting b with 2 pi r over n. And the area of the disk, or sorry, the area of the circle was n times the area of a slice. So it becomes n times this thing. By the way, notice that you can simplify a little bit because you can cancel the 2's here. So you get pi r over n times r squared minus 4 pi squared r squared over n squared. Are there any questions up to this point? Is it making sense? So far, so good. And now this something really cool happens. There are a couple of simplifications that you can do here with this expression. What's the first simplification that you see here that I could do? Okay, everyone, you kind of did say the two things that we should do. We can cancel out the n's, right? So you see that there's some n's here that go away, and there's an r squared and an r squared here. So you can factorize it and pull it out of the square root. And when you pull it out of the square root, you can take it out as an r. So let me just color. Okay, perfect. And let me change to this. So you get pi r. Let me put this like this. I'll put pi r. There's another r that you get by pulling out this r inside the square root. So I'll do that in a different color. So the area of a circle is starting to look like what? Area of a circle is starting to look like pi r squared times square root of 1 minus pi squared over n squared. Is that making sense? So far, so good? And okay, you should start noticing that this starts to take the flavor, right, of what, like the formula for the area, right? Because like the area of a circle is pi r squared, right? So we already have it. It's just that we have this chunk, right? There's slightly something else that pops out, which is not kind of what we're used to, right? But so what's going on here? Like the thing is that this formula is kind of like what we got from an approximation when we made n slices, right? But you have to imagine, right? Again, this is like a better and better approximation the more slices you make. Because the more slices you make, the difference between the triangles and the pizza slices get better, get smaller and smaller. So you have to imagine that you're kind of like calculating this for n equals 2, n equals 10, n equals 100, n equals 2000, right? So in fact, like we should go to Wolfram Alpha because I also think it's useful to show you that right now. So Wolfram Alpha is very useful for these classes. I don't know if I imagine some of you have already used it in the past, right? But So what we're dealing with is something like pi r squared over n squared. Okay. Oh. Pi squared. Right. This is kind of what we're seeing that. Like, let me see if I can just put like n equals 3. Oops. Okay. Can I put it like this? Oh, okay. Let's see if this works. Okay, no. It's I have to plug it in. Okay. Oh, okay. Sorry. Okay. Is that I have to insert like bigger numbers for this to work? Is that going to approximate this? Okay, it's not giving me approximations. Okay, this is a color. It's not working the way I expected, so because it's not giving me the actual values like as I wanted them here. Okay. Just give me a second. Yeah, usually we just give you like okay. I'll do it this way. Let's see. Sorry about that. Okay, perfect. Now this is going to work. Okay. So yeah, on GeoGebra, like what I wrote is kind of like this expression that we had on the multiplying pi r squared. So I'm going to plug in certain values just to give you an idea. So for example, if you plug in f of 7, meaning that you substitute x with 7 here, that gives you 0.44. If you put f of 10, meaning that you're replacing x with 10 here. So that gives you, that means this is what you would get for when you made 10 slices. You get 0.78. Then if you put f of 14, you get 0.89. F of 20, you get 0.95. F of 36, you get 0.98. F of 98. Okay, you actually don't get 1. You get something very, very close to 1. So like I should put, okay, let's put f of 50. So just to go back to like what I'm trying to say is that maybe I shouldn't have done this special mini detour into let me work from the app. Okay, what I'm trying to say is that this expression, right? In this expression, you are supposed to imagine that you're putting larger and larger numbers of n here because you're making more and more subdivisions, right? So as you make more and more subdivisions, you're increasing the denominator, right? So when you divide by a very large denominator, this starts becoming very, very small, okay? As n gets large enough, gets very large. Okay, and once you have that, so what we are going to end up saying, and this is my whole point of how this is related to calculus. So what we end up saying is that in the limit, which I'll explain in a couple minutes, in the limit of n goes to infinity, what you want to say is that that goes to 1. So like the idea of calculus will be to say that limit as n goes to infinity of 1 minus 4 pi squared over n squared is root of 1, which is 1. And that's how you end up with the formula for the area of the circle to be pi r squared times 1. And in other words, pi r squared. Is that making sense? Okay, so, but I mean, you should really, this kind of example tells you a lot of like what's going on in this course. So first, like, just to summarize what happened, like I was trying to find the area of a disk or a circle for which I don't know the answer, but I do know the answer for the area of triangles, right? So the idea like of what we just did was kind of like to approximate the area of the circle by the area of a bunch of triangles, which were these pixel slices, because that's something we could understand better or easier. And as you took more and more pixel slices, which is again this limit process, which is like the key idea of all calculus, as you take more and more pixel slices, then this is like a better approximation, and then the area, like the area that you care about, is can be computed with the help of this calculation. Okay, and what we'll do towards the end of the course is like, for example, for these problems about the areas, in this case, like using triangles is not that convenient. So what you end up doing is like approximate this by areas of rectangles. Okay. And again, like the approximations are not that great, but as you start shrinking the rectangles, the approximations get better and better and better. And so the way to compute the area for this region will be by like computing like areas of rectangles where the rectangles start like you start shrinking the rectangles and things like that. And all the calculus idea is basically the same idea over and over. You kind of approximate the object that you want to study by objects that you understand better. Okay. In fact, I should write that down. Every single problem in calculus kind of has this form, like, so you approximate. Oh, that's actually what's called a Riemann sum. Yeah, good question. Approximate an object you want to understand by objects you know better, and then take a limit. And what I have to explain to you is what it means by limit. Okay, so let's take like a 5-minute break just for people to get, because like now I'm going to do like a mini change of topics. So just for people to go to the bathroom, take some water if you want. And then once we get back like 12:10, I'll tell you, and we'll get more like properly start the topic, the beginning of the course, which is what limits are. But hopefully now you have like a little bit of a glimpse. But I'll do this in a slightly different way. So let's reconvene like in 5 minutes if that sounds good, and I'll keep talking about this. I'll pause the recording for now. So far so good. Everyone is back. Is audio okay? Okay, perfect. So now let me tell you more, something closer to what we will be doing this week, which is the other big problem that calculus was solving. So the first problem is this problem about computing areas, which I already told you a little bit about. The other problem is the problem about finding tangent lines. So that's actually what we will start with the course. It's just ironically, historically, this problem about finding areas kind of happened first, but So problem 2 that calculus was trying to solve, is to find tangent lines. Okay, so what I mean by this is something like what you'll see in this picture. So you have, let's say you have like a function y equals f of x. Right, remember the graph of a function is some sort of curve, right? So the idea is that we want to find, say, at a given point on this curve, like a line that looks like this. I'll be more precise, but like the idea of like a tangent line is kind of a line that gives you the direction of a curve. So this is like a tangent line. So this is a line that gives the direction of the curve. And maybe at a different point, the tangent line will look like will change. In fact, like it's not the same line that works all the time. And here, at a different point here, the line will be this one, for example. Okay. So in fact, let me see if I can show you this animation just to make things more useful. So let's see. Okay, so yeah, let's do this because this is really cool to actually see it moving. So on GeoGebra, you have this option to create a slider. You'll see in a moment. Let's call it F. Yeah, this is okay. So I just created a slider. That's something I can control from -5. By the way, GeoGebra can be downloaded for free. I'll send you the link probably after class so that you can play with it. It's very useful to just gain intuition about what's going on. So it's nice to have. Okay. And I'll give you like a function like f of x equals like x cubed minus x. Okay. And part of like what we'll do in this course is kind of just to learn why the graph of this function looks this way. That's actually one of our goals, like to understand why the graphs are what they are. So there's like an option on GeoGebra that you can, you enter tangent and then I'm going to use the point A and the function is going to be f. Okay. Let me change the color here. Let's use blue. Okay, so right now this animation is showing me like let's see, it's showing me the tangent line to the curve at when x equals 1. Why is x equals 1? Because I'm choosing the value of x to be 1 here, or the value for a. But if you change the value for x, you know, in fact, like I can show you, let's see. Right, so I'm moving the point on the curve. Maybe this is more convenient. So I'm moving the point on the curve by controlling this value for a. And as I move the point on the curve, the tangent line is changing. Is that making sense? So far, so good. And what we're trying to develop is a way to find all these tangent lines. But like what I'm trying to convey at this moment is that the line that what this tangent line is supposed to be will depend on the particular point on the curve that you choose or in the graph of the function that you choose. Okay. In fact, just to make this a little bit better. Okay, I'm changing the graph of the function a little bit. Perfect. So far, so good. So why? So the first question that you can ask is why do you care about finding the tangent lines, right? Let's stop showing this. So if you think of this think of this graph as some sort of roller coaster, right? Or like some sort of terrain, right? So if you think about the graph in this way, there is like kind of like you know, if you think you were climbing the graph or climbing this curve, like there's kind of like a top of the, there's some sort of like top of the mountain, right? Which is you kind of see here, and there's like kind of like a bottom of the valley that you see on this picture on this side, right? So what I'm trying to say is that kind of like there's this notion of a maximum or a minimum that the function takes, and they kind of correspond to like the peaks and valleys of the graph of the curve, if that makes sense. So for example, just by, let me see if I can show you here. The grid may make it easier to locate. So what would you say, where do you think the mean is taking place? Or the bottom of the valley? Like, I wrote that in the chat. For what value of x? Yeah, it looks like x equals 1 should be where the mean is happening. And where would you say the max is taking place? Like the top of the mountain, right? Where is the value for x in that? -1. So it looks that -1 and 1 are special values in this for this function, right? And let's try to see if we can identify something about the tangent lines in this case, right? So this at 1, this is how the tangent line looks, right? And then -1, oops, that's how the tangent line looks, right? So so let me put the other one. So I'm showing you right now the two tangent lines that take place at the max and the min, right? And if there's, let me see if I can put it here, and then the other one is y equals 2. So, okay, so these are these two tangent lines. And so the question is, what makes these two tangent lines special with respect to all the other tangent lines that I'm showing to you? What do you think is like a characteristic that these two lines have that none of the others have? Right, it seems that there's no inclination, right? So another way to say no slope is that actually the slope is 0, right? So m equals 0. If you remember, m was the letter for the slope. So it looks like the max and the mean occur where the slope equals 0. Okay, is that making sense? And more or less that's kind of the case. So one of the reasons why calculus ends up being useful is that once you have like a formula for the tangent lines, when you set the tangent line equal to 0, you'll find where the max and the mean of the function is occurring. So there are many applied problems that we'll do later in a couple of days, which are called optimization problems. And so it's kind of like, well, you're building like a product, a can of Coke, like like, you know, a Coca-Cola can or whatever that you're trying to sell. But to build it, like, you know, you want to maximize profits, right? Because if you are like a company, you want to make as much money as you want. So you have like a profit function, and you want to know for which values is your profit as much as possible. So you're trying to find the maximum of that function and things like that. So many calculus problems, again, like they just end up taking the shape of like finding tangent lines. And that's more or less like how Newton, well, I mean, Newton was one of the first people to develop calculus as we understand it. And the reason he was doing that is that he was creating like physics, I mean mechanics, and so like this famous Newton's laws of x, force equals mass times acceleration. And what happens is that to find the velocity of a particle or like the acceleration of a particle, you kind of can think of this as finding certain tangent lines, and so that's how this ends up being related to this like physics style problems about finding velocity and acceleration. So let me go back to the tablet. Okay, so what I'm trying to say is that these tangent lines will be related later to finding max and min, and related to finding max and min of a function. Velocity, acceleration, etc. We'll see many applications of these things. Okay, so maybe just to finish today, I'll just show you how to find the tangent line in a very specific example. Okay, and like we'll retake this tomorrow, and with this idea of finding limits. So let's say I give you something that hopefully you recognize, like y equals x squared. So that's a parabola, right? So on the parabola, right, you have this point 2,4, right? Because if x equals 2, then y is the square of x, so it just gives you 4. So what I'm trying to do now is actually trying to find, right? So my goal is to try to find the equation of this tangent line, right? Okay, and let's ignore the word tangent for a moment. What do you need in general? What do you need in general to find the equation of a line? Anyone remembers like the format for what's the equation of a line? Right, y equals mx plus b is one way to write it. There was another way to, okay, so let me put it in two different ways. Is y equals mx plus b, that's one way to write the equation of the line. Wasn't anyone remembers a second way to write it? Let's say if I knew like a point x naught, y naught on their line. There's another way to write it down. That is also another way to write it, but it is less useful for my purposes. There's an equation. There's a way to write the equation of the line which involves x naught and y naught, called the point slope form, I think. That's the name that people give to it. Yeah. Excellent. So one way to write the equation of a line is that y minus y naught equals perfect. I want to use this one. times x minus x naught. So these two are valid options. I mean, there are two alternative ways to write it. Depending on what data you have, one is more convenient than the other, okay? The thing is, like in the case of our parabola, right? If you go back to the parabola situation where I gave you y equals x squared, I'm already giving you a point on the I'm giving you a point where I want the tangent line to pass through. I'm looking at the tangent line that goes through the point 2, 4. Okay. So what I'm trying to say is that this is kind of in our problem, this is like our x naught, y naught. So the equation of this line for us should be like y minus 4 equals m times x minus 2. Is that making sense? So really what I'm trying to say is that the only thing that we actually need to find in this problem is the slope. If we knew the slope, we would have everything else to write the equation of the parabola. So the only missing piece as of now is the slope. Is that making sense? Okay, and how do you find the slope? This is again like the idea of calculus of approximating the thing that you want to find. So what we're trying to find is the slope. And to find that slope, we're going to approximate that slope by other things that we understand better. So let me just go back to GeoGebra to show you what I mean by this. Maybe I can undo this. Okay, so yeah, we have, oops. Okay, so we want the tangent line to at the point 2 of f. So this is what we're after, right? This is the line that I'm showing you here. So this is the point 2, 4. So just to compare with what I'm doing on the notes, the tangent line, I think I'm using blue for it. This I'm doing it in purple or like some sort of pink. Okay.
Professor, I got a little bit lost. What was it you wanted us to do right now?
So we're trying to find the slope of the tangent line. So I'm trying to find the slope of this blue line, if that makes sense.
Pardon? You cut out.
So I don't know if yeah, my answer was cut. Like what I'm saying is I'm trying to find the slope of this blue line. Is that
All
making
right.
Yeah.
Yep.
So good. So because once you have the slope, you have everything else about the problem. So what are we going to do to find the slope? So let me see if I can make my slider again. Okay. Okay, so what we like, this is like again like the cool idea about calculus. What you do is like, well, you take another point on the curve, okay, and when you take another point on the curve, once you have 2 points, there's a line that connects them, right? Just to make it more, to emphasize this more clearly, I don't know if you see there's like a line that connects these 2 points. The point that we care about, which is the blue one, and this random point, which is the black dot, right? So there's like a tangent line for this one, and you'll see in a moment that's the slope of this. Sorry, not a tangent line for this one. There's a line that connects these 2 points. and the slope of this line is easy to find. We'll find it in a second. So the idea of calculus is that what happens, right, as you start moving the black dot towards the blue dot, right? I don't know if everyone can see it here, but as you start moving the dot, like the black dot together to the blue one, like the lines kind of start looking more and more like aligned with one another, right? In fact, that actually happens whether you choose like numbers to the left or to the right of the line. It's just like it's a little bit harder to see here. So if you move the black dot to the blue dot, there's less of a difference between the black line and the blue one. Is that making sense? So what we're going to do is kind of compute the slopes for these intermediate lines, and then the slope that we actually care about will be kind of like a limiting slope, if that makes sense. Okay. Is like the idea kind of making sense? So it's kind of like compute the slopes of lines that you don't care about, but once the point gets closer and closer to the one that you care, like this is a better approximation. Okay, so let me write that down on the iPad to make it this more clear. So what I'm trying to say is that what we have is what I'm doing is that it ends like I'll end it like in 20 more minutes at most, and then I'll do the office hours. The Zoom meeting ends at 3:30 just because of the office hours. But yeah, we have like I'll finish in less than 20 minutes. But yeah, usually the latest would be like 2:55, 2:50. So what I'm saying is that you have this point 2, 4, and what we're going to do now is that I'm going to choose like an intermediate point, which is x, which I'm calling x. Oops. In fact, let me call this point like with green. And once you do that, yeah, I should probably move this a little bit so that it's more clear. Okay. Oops. Yeah, I'll upload the notes from the iPad as well. Okay, so there's this green line, which you can think of an auxiliary line, right? But my claim is that the slope of this line is easy to find. What is the slope of this green line? What is the formula for the slope of this line, of the green one? In terms of x, right? Because it will depend on x. Right, so remember this formula for the slope, which is kind of what, rise over run. So you subtract, you compute the difference in the y values, right? So the y values are x squared minus 4. And divide that by the difference in the x values. So the x values are x minus 2. Is that making sense? Good. And now this is the reason why you take pre-calculus or however you call it before coming to calculus, because the idea is that now you can simplify this expression. So is there a way to simplify the numerator? What can you do to simplify the numerator? Right, you can do the difference of square formula, which I'll write here as a reminder. There's this formula that says that a squared minus b squared is a minus b times a plus b, right? So if you do that for this problem, you get x minus 2 times x plus 2, right? Divided by x minus 2. And so what happens by doing that is that now this term appears both in the numerator and the denominator, right? So you can actually ignore it. So the slope of this auxiliary line is just x plus 2. Is that making sense? Are there any questions up to this point? So far, so good. Okay, but again, this is the slope of the green line. We don't care about that slope per se. We care about the slope of the tangent line, right? Which I'm drawing here on with my pointer laser. But the principle is that if you start moving, right? Like the idea is that if you start moving this point X closer, I don't know if you can see the arrow on the tablet, but if you start moving the point X closer and closer to 2, right? Then this slope will become better and better approximation for what the actual slope is that we want. Okay, so what should be the answer? Right, so as we move closer to 2, as we move x closer to 2, x plus 2 gets closer to what? It just gets closer to 4. And in fact, tomorrow, because I'll start this tomorrow, in fact, the way we will write this more precisely, all that I have been doing so far is to say, this is what we will write tomorrow, next time, is that the limit was as x approaches 2 of x squared minus 4 over x minus 2 is the same as the limit as x approaches 2 of x plus 2, right? And this is going to be 4. So all of this that we just did is exactly what we will rewrite tomorrow using limit notation. So this LIM just means limit. And again, I'll explain that tomorrow. But so what that means is that the slope should be, the slope of the tangent line should be then just 4. And once, if you believe that, you just go back to the equation of the line that I had given you. Sorry, let me bring this copy pasted here. So if you substitute that into what we did before, you will get that the equation of the line is y minus 4 equals 4 times x minus 2. Or if you want to simplify, I mean, you can rewrite this a little bit better. You can say that this is 4 plus 4x minus 8, right? Or that y equals 4x minus 4. So this should be the equation of the tangent line. I mean, any of this is the equation of the tangent line. Depends on how you want to rewrite it, but this should be the equation of the tangent line. So just to show you how this looks like, sorry, to go back to GeoGebra for a second. So what I'm saying is that you have this point 2, 4 that you see here. You have the point 2, 4, and then if I write the equation of the line, which was y equals 4x minus 4, you see that it kind of looks like what we would like the tangent line to look, in the sense that if you start zooming in, like, the idea of a tangent line, I should have said this a little bit more precisely before, but the idea of a tangent line is that if you zoom in enough, kind of it's like the difference between the curve and the line is it starts getting smaller and smaller. So it is kind of like the if you wanted to approximate a curve with a line, the approximation you should make is like that of the tangent line. Okay, but you have to zoom in, because if you don't zoom in, obviously there are bigger differences between the curve and the line. It's just as you start getting closer and closer to your point in question, then the difference gets smaller and smaller. But this is literally what you just computed is what's called a limit. So what I'll do tomorrow is kind of explain what these limits are, how you compute them in general, but it's more or less what we just did, just like in slightly more complicated situations, because the algebra will be trickier. But it is the flavor of the computations are more or less always the same, how they feel like. Is that making sense? Let me just go to the iPad again. And this slope is also called a derivative, but I'll tell you once we get to derivatives, we also see that, but I'll just make a remark. Before we finish today. It's also called a derivative. Okay. Is that making sense? So yeah, this is roughly what I wanted to tell you about today. So I don't know if there are any questions before we end, if it's okay. So far so good. Well, not, I mean, the limit question, like what we just did, like you are expected to find limits. So yeah, like a very common question is to find the equation of a tangent line. This question, the area of the circle question, is not one that you have to worry about at the moment. But the one that I just did, that's more close to a typical question. That there's always like a question on every calculus exam that asks you to find the equation of a tangent line. So yeah, it's just that probably the equation of the function will be a little bit more complicated than y equals to x squared. But it's definitely like an example that you have to understand as like as the course progresses. But yeah, like the first derivation of the area circle, I think that is one you don't have to worry about. I just find that that's kind of useful because it gives like a good idea of what like how these things work, of approximating things, areas or what have you. Any other questions? So okay, so the homework, there's like one assignment is just like pre-calc stuff, like saying what the domain of certain functions are, is, things like that. That, I mean, hopefully, I think it's kind of straightforward. The second part of the like the other homework is more on limits, so I would say don't worry about that one until tomorrow. But like one of the two should be doable right now, and then the other one, like tomorrow, the second assignment should be all of it. You should be able to do after what we say tomorrow. And then again, even in this pre-calc stuff, yeah, most of it is kind of elementary, but if you're getting stuck, you can always ask me about it. It's more like a refresher of certain things you should know. But, and again, like as we go on, I'll also bring, if there's a property about sines or cosines or other things that you need to remember, I'll bring it up in class before we use it. So I'll always be reminding you of certain properties, like for example, the difference of square formula and things like that. I'll be telling you what are the important things to keep an eye on. Any other questions? Okay, so what we'll do is like, I'm going to close this Zoom meeting just to save the video on my computer, but then I'll join it again like in 5 minutes or so for the office hours. So if someone wants to come to today's office hours, I'll be here like until like 3. I mean, if no one comes, like I'll probably finish it a little bit earlier, but in principle, I'll always be here at least until 3:20 or something like that. So I'll just log off so that the video gets recorded to my computer, but then I'll rejoin this Zoom chat like in 5 minutes if someone needs to ask me questions on during office hours, if that sounds good. Otherwise, if not, I'll see the rest of you tomorrow, and I'll send you a link soon with the recorded video and the notes for the iPad as well. Okay. Okay, good to see you. Bye.